Okay, we're ready for Lecture 31 in AP Statistics. Again, I'm not affiliated with the College Board. This is Dr. Kling, and today we're going to introduce t-tests, or t-intervals. We use these with quantitative data. Remember, that's data that can take on many values. It's measured in things like inches or seconds or pounds. And I'll use an example, SAT scores. Suppose that in our state the average verbal score is 540 and we want to compare our school with the state. Okay, so that might be an example. Now, here's some stuff you don't have to take notes on, but if you're ever curious, sort of why we talked about the normal distribution a lot, and now all of a sudden we switch to something called t-distributions. And why do we do that? It has to do with the fact that we are taking our estimate of the mean, x bar, and our estimate of the sample standard deviation, s, from the same sample. Again, this is just for your information. You don't need to take notes. So what that does some strange things, because we're passing through the data twice. First, we pass through to get the mean, x bar, and then we take the sample standard deviation around x bar. So if we had two different samples of data, imagine two seesaws, and we use one seesaw to get the measure of the mean, and then take that mean and put it over here to get standard deviation, we would be fine. But we're using the same data to get the mean and the standard deviation, and so that gives us some peculiarities. The the sample mean is simply the sum, this is a summation sign, of all the values of x. That is, we'd add up, let's say we took a sample of 15 students, their verbal SATs, and let's say the average was so we take the first one, it's 520, the second one's 590, 610, and we just add them all up and divide by the total number of students. Pretty intuitively obvious. But the sample standard deviation, if we were taking a standard deviation around the true mean or some other mean, the sample standard deviation would be the square root of the sum of xi minus mu squared over n, but we don't have the true mu. So we don't have it. We use instead this sample x bar, and when we do the x bar, the formula for the sample standard deviation will be square root of the sum of the xi minus x bar squared over n minus 1, because we've used up, so in some sense, one unit of data to compute x bar. Now, this concept of using up some data, it's called reducing the degrees of freedom. And this concept of degrees of freedom will show up in the t-distribution. So when instead of the normal distribution, which is the same for any sample size, we will find that the degrees of freedom in using a t test, the degrees of freedom is equal to n minus 1. So if we look at a table of t-distributions, we will see this column labeled df for degrees of freedom, and then in our work that'll be n minus 1. The sample size minus 1 will be the degrees of freedom. As the degrees of freedom get larger and larger, as the sample size gets larger and larger, the t-distributions will start to be less variable and will converge to the normal distribution. Okay, so it is worth taking notes to note that the degrees of freedom is n minus 1. That's something you should have in your notes. Okay, so let's then let's start with a t interval. So let's assume that for our school we take a sample of 12 students and we get a sample mean of 571 and a sample standard deviation of 45. And what did I say that okay, so now we want to find, let's say we want to find a 90% confidence interval for that. We're just going to stick this into our calculator. We're going to look for a t interval, and we'll just stick all this information into the calculator and see what comes out. Alright, hang on a sec. Okay, so we'll do stat tests. We don't want that. Where is it? Stat tests. There we go. Now we'll do t interval. Where's t interval? Okay, t interval. And we need to input some stuff. We'll do stats. We'll go down to x bar is 571. We have s is equal to 45. N is 12. Confidence level is 90.90. And we go down to calculate. Okay, and it says the interval is 547.67 to 594.33. 547.67, 594.33. So that would be a 90% confidence interval using these t methods. And that's kind of what you really need to know about calculating a t interval. Let's say we wanted to test let's say our null hypothesis is that our mean is equal to the state's mean. And what did I say the state mean was? 540. So mu equals 540. And the alternative, let's say, is that our mean, we're doing better than the state average. And I'll tell you that because the state average is outside the confidence interval, I'm pretty sure we're going to reject the null hypothesis at something like a 5% level of significance. But we could go ahead and do the test. Well, it's probably sitting in the calculator anyway, so let's do it. Stat tests. And now we'll do a t-test. And our data already sitting there. Our null hypothesis mu naught is 540. We have our x bar, our s. Sample is 12. Our alternative hypothesis is greater than 0, so that's okay. So we just need to calculate. Calculate. Enter. Okay, and we get a value, something called t of 2.386, and we get a p-value of 0.0108. Let's see if we can remember that, and go back to our chalkboard. Okay, so now we have a t-value, which I wrote down here, of 2.39, and that's a little bit like an x bar minus mu over s. That's kind of what it is. That's our sample mean minus the null hypothesis mean over the sample standard deviation. And then the p-value was 0.018, and 0.018 is a small number, less than 0.05, so it's consistent with this notion that we reject the null hypothesis. So that's a low p-value. The p-value comes from taking, instead of a norm CDF, a t-CDF, from the t-value, the 2.39, to some big number, 10. And then this third thing is degrees of freedom, which is the sample size minus 1. Remember, degrees of freedom will be the sample size 12 minus 1. We plug that in over here, and that's how the calculator calculates a p-value. You don't really need to know that because the calculator is doing that. And I want to mention the next topic, which is this issue of sample size. If the sample size, well, I'll talk about that next time. How about that?